This is Adel Gastli. I'm going to present to you part 1 of the chapter about transformers. In this part, I will go through a short introduction of the transformers, and then I will present their construction and principle of operation. A transformer is an electrical device that transfers AC energy from one electrical circuit to another by magnetic coupling, but without any moving parts. Its action is based on the laws of electromagnetic induction, which we have covered in the previous chapter about magnetic circuits. There is no electrical connection between the primary and secondary sides, except for one case of transformers called the Autotransformer. During this AC power conversion process, there is no change in the frequency of the voltage. The AC power is transferred from the primary to the secondary through the magnetic flux. Transformers are rugged and durable in construction. They also have high efficiency, as high as 99%. Transformers alone cannot do the followings. They cannot convert direct current to alternating current or vice versa. They cannot change the voltage or current of DC power. And as we have seen previously, they cannot change the frequency of the AC's power. However, transformers are components of the systems that can perform all these functions. Transformers are used with different sizes and for different applications. They are used in small power supplies to step down the voltage to lower values that are useful for electronic circuits. For instance, we find them in computer power supplies, in TVs, in DVD recorders, etc. Transformers are also used in the power system at different levels. These transformers are much bigger. For instance, they are used to step up the voltage and the output of the power plant to boost it to very high level of few hundred kV for the high voltage transmission of electrical energy. At the end of the transmission, the voltage must be stepped down using step-down power transformers, which adjust the voltage to a lower level called medium voltage, which is about few kilowatts. When we reach close to the low voltage consumers, this medium voltage must be stepped down further to lower voltage of few hundred volts for the distribution network. This photo shows a large transmission transformer used for boosting the voltage to very high values, few hundred kilovolts. This photo shows an example of distribution transformer which steps down 220 kilovolt to 5 kilovolt. These are examples of service transformers, 11 kilovolt to 415 volts, and circuit transformers which step down to the low voltage to much lower voltage to be used for electronic circuits. Now, let us look at the basic elements of a transformer. The basic components of a transformer are the iron core, the primary winding connected to the source, and the secondary winding connected to the load. Both windings are made of insulated copper wire. Note that both coils are electrically separated but magnetically linked through a low reluctance path, which is the iron core. Laminated iron core is used to reduce eddy current losses. The insulation film between the laminated iron sheets will create a very high resistive path to the eddy current, which will reduce it. Next, I will explain to you how the basic transformer works. For that, I will use the two-winding theory. However, before doing that, I will first show you a movie that you can find on YouTube at this link, and that explains well how a transformer works.
In this video we're going to be looking at transformers, and here's an example from my microwave oven. It consists of two coils, a primary and a secondary, and these are surrounded by a very substantial piece of iron. The iron actually goes through the middle of these two cores, and this is something what we call an E-core. It forms an E-shaped with an end plate on it. The primary is much thicker wire because it carries more current, and the secondary has a lot more windings on it, and we'll see why later. But basically this transformer has 240 volts in and around 2000 volts out. It's what we call a step-up transformer. So what we'll do is have a look at how does this thing work. A transformer relies on two key physics principles: electromagnetism and electromagnetic induction. Electromagnetism is when an electrical current generates a magnetic field. Electromagnetic induction is where a magnetic field causes an electrical current to flow. As you can see, one is just the reverse of the other. The basic transformer construction consists of a primary coil magnetically linked via an iron core to a secondary coil. The primary coil generates a magnetic field, and the secondary coil converts that magnetic field back into a flow of current, or a voltage. So if we look at what goes on in a wire when we pass a current through it. When we pass a current through a wire, the red arrows representing the increase in current flow, a magnetic field is formed. To get a stronger magnetic field, we get more current to flow through the wire. Alternatively, what we can do is use two wires. Doubling the wires effectively doubles the current flow past a certain point, and therefore it doubles the magnetic field strength. We can use this in a transformer to make some very strong magnetic fields by using a coil. We can use this principle of multiple wires to greatly increase the strength of an electromagnet. By looping a wire into a coil, the same current carrying conductor passes the same point repeatedly. The magnetic field from each wire effectively adds together and makes for a very strong magnet. So if we look at what goes on in a transformer core, if we start with our coil of wire, if we now take a cross section through the coil and only consider the wires going into and out of the screen. By convention, we represent objects going into and out of the page using dots and crosses. And imagine an arrow being fired from a bow. If you can see the cross of the feathers of an arrow, it's travelling away from you. If you can see the point of the arrow, it's heading towards you. We can now add the magnetic field of each conductor as we have seen previously. The magnetic fields actually add together, creating one larger magnetic field, and we can represent this with field lines showing the combined or the resultant magnetic field. What we can then do is wrap this coil around an iron core instead, or a loop of iron. Now when we do this, because magnetism passes through iron much better than it does through air, we actually find that the magnetic field is constrained within the iron core. It permeates the iron core. Permeates just means travels through, basically. Iron can be several thousand times better at conducting a magnetic field than air. So if we now look at the primary side of the transformer, we can see how we generate this magnetic field which passes through the secondary coil. And what we'll now look at is induction in the secondary coil. The principle of induction involves moving a magnetic field past a conductor. In this view, as we move the magnet through the wire, some electrons move. We move the magnet the other way, and the electrons move in the opposite direction. The key thing is if I move the magnet faster, more electrons move. So the faster I move the magnet, the greater the current flow. But key to this is that it's a moving magnetic field that causes the electrons to move. In other words, a changing magnetic field generates a current. So let's have a look at that inside the transformer. First, looking at the primary side of the coil, the red arrows represent the magnitude of the current, so bigger arrows, bigger current. I increase the voltage, the current increases, and I get a growing magnetic field. But once the current is the same, the magnetic field is static, it stays the same. So let's look at that again. Increasing voltage, increasing current, changing magnetic field, voltage stays the same, current stays the same, magnetic field stays the same. The key thing is, the voltage is only induced in the secondary coil when the magnetic field is changing. So as long as the magnetic field is changing, we've got a voltage in the secondary coil. But once the magnetic field stays the same, there's no voltage induced. So just watch that again. Changing magnetic field, we have a voltage in the secondary, but when there's no change in magnetic field, we have no voltage. So what we actually need is an input voltage that changes constantly. And we can do this using a sine wave. As you can see, the sine wave constantly changes voltage, which constantly causes a change in magnetic field, which means we're always going to have a voltage induced on the secondary. So we now have seen how a voltage and a current flow can be induced in the secondary. The induced voltage depends on the strength of the magnetic field and the number of turns on the secondary coil. More turns on the secondary will generate a larger voltage. The strength of the magnetic field, though, depends upon the number of turns on the primary. So the voltage output of a transformer depends on the relationship between the number of turns on the primary and the number of turns on the secondary. So let's now have a look at that relationship. This is the transformer formula, and it's one that you need to know. It simply tells us that if we take the ratio of the voltages, secondary divided by primary, it's the same as the ratio of the turns, secondary divided by primary. Easiest way is to go through some examples. If we take 10 turns on the primary and 10 turns on the secondary, we look at the ratio, secondary divided by primary, and it's 1. 10 divided by 10 is 1. If we put that into our formula, and then rearrange the formula, what we know is that the output voltage on the secondary is 1 times the voltage on the primary, or that actually both voltages are equal. So equal number of turns, equal voltages. 240 volts in would give us 240 volts out. 10 volts in would give us 10 volts out. If we look at a different example where we have 10 turns and 5 turns, we now have less turns on the secondary. If we take the ratio of that, 5 divided by 10 is 0.5. We put that into our formula, rearrange it, and this tells us that the voltage on the secondary, the output, is half of the voltage on the primary. In other words, the voltage has stepped down. It's a step down transformer. We have half the turns on the secondary, so we have half the voltage on the secondary. You can probably guess what happens when it's the other way around. Again, work out the ratio, put it in our formula, rearrange the formula, and this now tells us that when we have twice as many turns on the secondary, we get twice the voltage on the secondary. This is called a step-up transformer. So in summary, voltage causes electrons to flow. Flow of electrons is a current. The current generates a magnetic field. By looping the wire, we can increase the strength of the magnetic field. The magnetic field passes easily through iron, and changing magnetic field induces a current in a conductor. Therefore, transformers have to use alternating currents. They will not work if you just connect them to a battery. The output voltage is equal to the ratio of the number of turns multiplied by the input voltage, or in other words, the ratio of the primary and secondary voltages is the same as the ratio of the primary and secondary coils.
Let us consider the two-winding structure composed of a magnetic core and primary and secondary windings as shown here. The primary winding is energized with a sinusoidal voltage V1. There will be a current I1 flowing in the primary winding, which generates a flux phi in the core. Now, if we neglect the leakage flux in the windings, then we can consider that the same flux will cross both windings. This flux induces electromotive forces EMF E1 and E2 in the primary and secondary windings respectively. The EMF E1 in the primary winding is calculated as the product of the number of turns N1 in the primary winding multiplied by the derivative of the flux over time. Similarly, the EMF E2 in the secondary winding is equal to N2 d phi by dt. Now, since the source current is sinusoidal, then the flux will be also sinusoidal, which leads to these equation of E1 and E2. The capital letter E in E1 and E2 designate root mean square values. Notice that the waveforms of the EMFs E1 and E2 are in time phase because they are produced by the same flux. We can deduce the RMS expressions of the primary and secondary EMFs as shown in these equations. Now, if you consider the ratio of the primary EMF RMS value E1 over the secondary EMF RMS value E2, we can show that this ratio is also equal to the winding turns ratio designated by N1 over N2 or by the letter A. In conclusion, we can say that the voltages are in phase, so there is no phase shift between the both EF voltage at the input and the output. And the magnitudes of the voltage vary with the winding turns ratio. So the higher the number of turns, the higher is the corresponding voltage. Now, before determining the equivalent circuit of a practical transformer, let us consider first an ideal transformer. An ideal transformer is defined as a transformer with the following assumptions. The winding resistances R1 and R2 are very small, equal to 0, so they are neglected. There is no leakage flux and core losses are negligible. The magnetic core has very high permeability, so mu is almost infinity, which leads to a very small exciting current, close to 0, so it's negligible. Therefore, we can consider that the terminal voltages at the primary and secondary sides are equal to their respective induced EMF voltages E1 and E2. Thus, we can write that the ratio of the terminal voltages is equal to the turn ratio A, which is also called a transformer ratio. Considering the power conservation theorem, we can write that the input apparent power S1 equals the output apparent power S2. Using the complex vector representation of the apparent power, we can write that S1 equals E1 multiplied by I1 conjugate and equals S2, which is also equal to E2 multiplied by I2 conjugate. Note that all parameters used here are complex vectors with their real and imaginary components. Now, from this equation, we can deduce that the ratio of the primary current over the secondary current is equal to the ratio of the secondary voltage over the primary voltage, which is the same as the ratio of the number of turns N2 of the secondary winding over the number of turns N1 of the primary winding, which is actually the inverse of the turns ratio. From this equation, we can deduce that N1 I1 equals I2 N2, which means that we have conservation of MMFs. In summary, we can say that the currents are in phase and the current ratio is opposite to the voltage ratio. Another important circuit theory is useful for developing the equivalent circuit of the transformer, which is the impedance transfer theory. Let us consider such a circuit with two windings and where the secondary is connected to a load with an equivalent impedance Z2. Note that Z2 is not electrically connected to V1, but we can find an equivalent circuit Z1 seen from the source voltage that will give the same primary current I1. For that, let us consider the secondary circuit. So we can write the secondary impedance Z2 as V2 over I2. Based on the equivalent circuit, the primary equivalent impedance Z1 is V1 over I1, which can be rewritten as in this equation after replacing V1 as a function of V2 and I1 as a function of I2 using the turns ratio. Now replacing V2 over I2 with Z2, we can obtain the relation between Z1 and Z2. So Z1 equals Z2 multiplied by A squared. So it is possible to transfer or refer the secondary impedance of the transformer to the primary side. Usually when we transfer an impedance from one side to the other side, we denote it with the prime symbol. So the secondary impedance transferred to the primary side is designated by Z prime 2 and equals to A squared Z2. And the primary impedance transferred to the secondary side is designated by Z prime 1 and equals to Z1 over A squared. So depending on whether we want to do our calculations on the primary side of the transformer or on the secondary side, we need to transfer first all the parameters on the same side. This impedance transfer is very useful because it eliminates magnetically coupled circuit and transforms it into electrical circuit and thereby simplifies the circuit analysis. This is the end of this part. Thank you for watching.